Jeremy, do we want to move the camera over here?
Whatever you think is best. As long as the lighting's good.
Great. Hi everyone. Thanks for having me. I'm really excited to be here today. I'm going to talk about some of the new stuff that we actually just released 2 days ago. So this is, I think, the first public talk on this stuff. So just intro, I'm right now chief scientist at Together AI, also an assistant professor at Princeton. And I'll talk about optimizing attention for modern GPUs. Okay, so just to motivate some of the why we want to do this stuff, why we want to speed up attention. So the problem we're trying to tackle is modeling long sequences, and on the application side, this. All right. Okay. Yeah, so on the application side, this can unlock a bunch of new capabilities. So for example, in NLP, we want to reason over long text for some books and places and code bases. That could be hundreds of thousands or millions of tokens. In computer vision, we want to model high-resolution images. So if you use something like Vision Transformer, high-res images is going to turn into long sequences. In a bunch of new areas like audio, video, medical imaging, data is naturally modeled as sequences of up to millions of steps. And so the dominant architecture right now, the transformer, has some difficulty working with such long sequences. And if we can make attention go fast, we can unlock some of these new areas. And efficiency is the bottleneck for modeling long sequences. So here's just a quick example. This is a while ago. I'm using this is Megatron LM, which is a code base from NVIDIA, used to train large-scale models, and I'm measuring on A100. So if you train a model with sequence length 2K, which was popular maybe 2 years ago, you get very reasonable training speed. But the moment you increase sequence length to 8K, your training speed drop by half or so, or you run out of memory. So if we can solve this efficiency problem, we can train models with much longer sequences. So this is just to motivate why we want to work on this problem. And so that's just motivation. And for the talk, I'll talk about Flash Attention 3, which is the stuff we just released 2 days ago. So I'll recap some of the core ideas of Flash Attention, and then I'll talk about how we optimize that for Hopper GPUs H100. And then I'll show some benchmark results. So just as a background, maybe a bunch of you are familiar already. So the attention mechanism, this is what we're trying to optimize. So as inputs, we're taking query, key, and value. The query and the key and the value have shared n by d, where n is the sequence length, usually on the order of thousands, and d is the head dimension, usually on the order of hundreds. And you multiply them together to get the score matrix, and this score matrix has size n by n. You do a softmax, you multiply by the value to get the output. And so we see that attention scales quadratically in sequence length because of these intermediate matrices of size n by n. So I'm just talking about a single head of attention here. This is why, ever since Transformer came out in 2017, tons and tons of folks have been working on making attention faster, approximating in various ways. Because, it scales quadratically in sequence length n. So if you double the sequence length, you need to do 4x more computation and 4x more memory. So it turns out the biggest cost is not so much in computation, but the biggest cost is in read and writing memory. So it's about moving the bits. And we want to figure out a way to not have to read and write these intermediate n by n matrices. So that was the idea from Flash Attention, combining kind of kernel fusion on the system side and softmax rescaling on the machine learning side that allows us to do this kernel fusion, but still get the right answer. So the idea is to compute things by block. These ideas are quite old, but with attention there are some challenges. For example, the softmax requires this kind of row-wise reduction, and that makes it hard to do kernel fusion. And in the backward pass, if you want to compute gradient, you presumably need to store the intermediate matrices n by n from the forward pass to compute gradient in the backward pass. So our approaches are to use softmax rescaling so that we can do tiling with blocks and then do rescaling to get the right answer. So it's a mathematical transformation of the algorithm, but still gives you the right answer at the end. And for the backward pass, we essentially do recomputation. The idea is you don't want to store large amount of information from memory and having to read and write that. Compute is cheap, so you want to you can recompute things and that end up being faster. So these are two key ideas, and with flash attention 1, I think we already had 2 to 4x speed up compared to baseline. And memory is now linear in sequence length, so memory savings is going to go up as the sequence length goes up. So that was maybe 2 years ago. Flash attention 1 was released 2 years ago, and then a year ago we released flash attention 2, which is more optimized for A100. But there's still a problem. So H100 is a challenge because the hardware is new. There's a bunch of new features, and the programming model actually changes quite a bit. So if we just use the old code from flash attention 2, we can only get to about 35 to 40% utilization. We can reach maybe 350 teraflops per second, while the H100 max flops is 900. Is around 1,000 teraflops per second. Right. So that is the goal we set out to do, which is to optimize attention for H100 for Hopper. I'm using Hopper as an example. Actually, other accelerators also have this kind of asynchronous programming model that will generalize. So this is joint work with a bunch of folks. Actually, started with folks from Kofax, Jay and Ganesh. There's Ying from Meta. We're very fortunate to collaborate with a bunch of folks from NVIDIA as well. Vijay and Pradeep. Pradeep is here, and I'm just doing cheerleading. Okay, so we want to optimize for H100. What are the new features of the H100 that we care about? There's some new instructions. So there's this warp group MMA that operates at the level of four warps at a time instead of just one warp. That gives you higher throughput. You kind of need to use that if you want to reach the max throughput. There's this hardware unit called TMA, Tensor Memory Accelerator, that lets you do memory loading between global memory and shared memory, and it saves a bunch of registers. So that's important. The other feature, the second feature, is asynchrony, meaning you don't want to have to issue an instruction and then just sit there and wait for it. You can issue an instruction like an MMA, essentially matrix multiply. While the tensor core is computing the matrix multiply, you can go compute something else like the softmax. And Hopper has a bunch of great features to allow you to program asynchronously. So this is the major shift in programming model from the more kind of synchronous programming model in Ampere to asynchronous in Hopper. And to explore that, we have a bunch of scheduling to overlap the matrix multiply and the softmax. I'll talk about why this is necessary. And low precision, FP8. So Hopper supports FP8. This would double your throughput, but it has a bunch of challenges on how you would quantize to reduce quantization error. Okay, so the upshot is once you do all this, you get about 1.6 to 2x on the speed up on FP16, and you get maybe 3x speed up on FP8. Okay, so I'll talk a little bit more details on how these things work. So the new instructions, work group MMA and TMA, you kind of need to use these things. Work group MMA is necessary. If you don't use it, you can only reach about 60-something% of peak throughput. The TMA is a hardware is a unit in the hardware that will accelerate memory copy between global memory and shared memory, and that saves you a bunch of registers because it does all the coordinate calculation and predication for you. So if you just switch to using these new instructions, you already get most of the way there. I think you can reach about 500 teraflops per second. So you go from 35% to like 50% utilization. But you can go much further. You can exploit asynchrony. So I'll try to motivate why you want asynchrony. So in attention, there are two main operations. One is the matrix multiply, so Q times K, or taking the the probability and multiply by b. So these matrix multiply that you need to use tensor cores for. But within the softmax, you need to do these things like exponentiation. You find the max and then subtract the max and exponentiate that. Turns out exponentiation is very, very slow or have very low throughput. Here's an example. I won't go into the details, but because the tensor cores are so fast, within one cycle, I think they can do around per streaming multiprocessor per cycle, they can do around 4,000 operations, right? Because these are specialized hardware units, essentially systolic arrays, to do matrix multiply. But to compute exponential, it has this multifunction unit that has much, much lower throughput. So the exponentiation has, like, I think 256x lower throughput, right? So even though most of the flops are in matrix multiply, because the throughput of the exponential is so low that it accounts for maybe 50% of the cycle, right? So if you don't overlap these two, you're gonna spend a bunch of time just idling waiting for the exponential while the tensor cores are not running. So we need to overlap them. And so I won't go into details of how we overlap them, but this is just to motivate. How exactly you do that, you have to play with the scheduler so that essentially while one work group is doing the tensor core to do matrix multiply, you want the other work group to do the softmax. And that gives you quite a bit of speed up. So for FP8, that would double your throughput, but you're gonna do a bunch of fancier quantization to reduce error. That I won't go into. I think it's maybe less interesting from a systems perspective, but more interesting on the machine learning perspective. So I won't go to that. The upshot is once you've done all this, you can speed things up quite a bit. So we see about 1.6 to 2x speed up in FP16, and we can reach up to 750 teraflops. So this is pretty much close to the speed of matrix multiply. So that's amazing. You have matrix multiply, which is probably the most optimized subroutine on the planet, and then now attention is getting close. With FP8, we can reach about 1.2 teraflops per second. So that's pretty crazy. And so just to summarize, so this is a fast and accurate attention optimized for modern hardware. The two main ideas are asynchrony and low precision. And with this, you can have faster training, better models with longer sequences. And so for the last couple of seconds or so, I just mentioned if you kind of enjoy this style of work at Together AI, so we're building a cloud for generative AI. So we do a bunch of stuff, not just low-level optimization, but also model design, architectures, research, and so on. And we're hiring a systems research engineer on GPU programming. So if you're interested, go on our website, Together AI. I'm also going to hang around, and if you want to talk to me about this. Right. That's it. Thanks.
A question?
Yeah.
Asynchronous. How backwards compatible does that code end up being, if at all?
It's not so compatible, so it won't run on Ampere. So Ampere, I think with Flash Attention 2, we pretty much reached the limit where it also hit like 70 or 75% util, so there's not a lot to do there. Yeah. Yeah.
Are there open issues or like PRs to go after for people in this hackathon in Flash Attention 3?
So we are still in the process of releasing the code. Some of the code is up there. We're still releasing it. I think it's a little bit too kind of in the weeds, I would say. But if you're interested, I would recommend going through the Cutlass tutorial. I think Pradeep just you guys merged the H100 Jam tutorial.
It's part of the. It's not yet released, but it's there as a PR.
Right. So I would say Cutlass. We build all this on Cutlass. Cutlass is a bunch of tutorials that you can go through as well. Yeah.
How much longer the code base became after you added the asynchrony? Like 10%, 20%?
I think it got shorter.
Oh, really?
Yeah.
Amazing.
I think Cutlass has built a bunch of abstractions that we can use.
Okay.
I think in Ampere, I wrote a bunch of things that I should have just called Cutlass, but now version 3, where we've got Kotlin people telling us like, hey, like we already wrote this, you guys should be using it. It makes it quite a bit more pleasant.
And was the growth in compile time due to like the added templates and abstractions from Cutlass?
I think this version is actually very fast to compile because we haven't added all the features like alibi and local attention and so on. So actually right now it takes like 30 seconds to compile. So it's not so bad. The one Ampere has a bunch of features that takes like sometimes like 5 or 10 minutes to compile.
Oh, wow.
Yeah, we're working on that. Yeah. Yeah.
When you're coming up with these creative ideas, like recomputation instead of storage, or like modifying scheduler, is there like a method, or if we're trying this or that to come up with something,
Right.
As useful?
Yeah.
What advice would you have in the process for generating the core idea?
Yeah, so my perspective, I come from a kind of machine learning background, and so the first time I talked to the systems people, kind of the biggest bang for your buck is profiling and benchmarking. Like the first time I talked to someone in the system, they're like, "Did you profile your code?" And that was just mind blowing to me. I did. I was like third year of my PhD, and I'm like, yeah, I've never profiled my code. Like I don't know where the bottlenecks are. I can prove to you that it should scale as n log square n something, but I don't know where the bottlenecks are. So profile your code. I think PyTorch has a great tutorial on just PyTorch Profiler. That's usually the first thing I reach for.
And when you're profiling CUDA code, how do you typically?
So PyTorch has a profiler. I think NVIDIA also has a pretty good profiler Nsight system for kind of a bunch of kernels, and then Nsight compute for one specific kernel that will tell you where the bottlenecks are. Yeah.
Last question.
Yeah, if you don't mind. So I see that from your presentation, the most of the performance gain you took from synchronous and overlapping.
Mm-hmm.
So how did you practically implement the overlapping so it actually worked? And at Insight, you saw all those kernels running in parallel instead of the hardware schedule puts everything in the queue, and the whole performance is just crap. Did
Right.
you use the Graph API for that implementation, or that's something else?
Right, so it's overlapping at the level of workgroups, so it's one kernel, but you have
Yeah.
two main workgroups running, and
Yeah.
it will not be apparent how they
Yeah.
actually overlap. We use some barrier or synchronization primitive like barrier sync to overlap that,
Mhm.
but I don't think there's a good way to visualize that right now.